Okay. All right, so go back to this here. Okay. So I want to, because I don't think we're finished with chapter. I don't think we're finished with chapter 8. So I want to make sure we finish that before we move on to chapter 7 in terms of the assignment. So can somebody remind me where we stopped the last time?
Part 3.
Okay, part 3. So now we're going to get into a discussion of empirical formula and molecular formula, and how do we determine the empirical formula based on percentage or mass data. Now, just to briefly review, firstly, let me talk about the molecular formula. So the molecular formula, of course, gives you information about the number of atoms of each element that is present in a molecule, right? So, for example, if you're given, put this in here. If you're given the formula for glucose, which is okay, so let's say you're given the formula for glucose, which is C6H12O6, right? So what that tells you is that for every molecule of glucose, there are 6 carbon atoms, 12 hydrogen atoms, and 6 oxygen atoms, right? So this is the molecular formula for glucose. The empirical formula, on the other hand, does not give you the numbers of atoms per molecule. What it gives you instead is the ratio of the atoms of the different elements present in the substance. So in the case of glucose, the empirical formula will be equal to CH2O, because what that tells you is that the ratio between carbon to hydrogen to oxygen is 1 to 2 to 1, right? So that's the difference between the empirical formula and the molecular formula. Now, if you know what the empirical formula is, if you want to get the molecular formula, you need an extra piece of information. And that extra piece of information would be what is called the integral factor. In some textbooks, they use the letter I to represent it. I'm going to use that. In other textbooks, they use the letter N. Doesn't matter really. But the integral factor is basically the molar mass of the compound divided by the empirical formula mass of the compound. Now, the molar mass is what you get when you add up all the molar masses of all the atoms present in the formula, right? While the empirical mass is basically the same thing, but you're applying that same idea to the empirical formula, right? Now, the thing about it is that the molecular formula divided by the empirical formula will give you an integer, right? That's why it's called the integral factor, right? And that integer could be literally any whole number, 1 through whatever, all right? So in the case of the glucose here, right? If I remember correctly, the molar mass is about 180. And in the case of the empirical mass, it is 12 plus 2 times 1.008 plus 16. So that gives you about 30, right? I'm just using estimates here, right? So in the case of glucose, the integral factor will be 180 divided by 30, and that will give you 6, right? So the integral factor is 6. So therefore, let's say you did not know what the molecular formula is, but you knew what the empirical formula is, and you knew what the integral factor is. Then to get from here to here, we simply multiply each of the subscripts here by 6, right? And that's how you get the molecular formula from the empirical formula, right? You're going to need the integral factor, right? So basically, the problems that we're going to look at here involves, to some extent, what we just talked about. In fact, the first question, let's look at the first question, 1A. It says, determine the molecular formula of each of the following compounds. Now, in this case, they gave you the molar mass, right? Which is this right here, right? And they gave you the empirical formula, right? So basically, you can use the empirical formula to find the empirical mass, the empirical formula mass. The empirical formula mass would be 1.008 grams per mole plus 12.01 grams per mole plus 2 times 16.00 grams per mole, all right? So we need to work that out. Let me work out what's in the parentheses first. Well, that's 32 plus 12.01 plus 1.008. So this works out to be equal to 45.02 grams per mole, right? So to get the integral factor I, that would be equal to the molar mass, which is given as 90.0 grams per mole, divided by 45.02 grams per mole, and that would approximate to be equal to 2, because I must always be an integer, right? So therefore, the molecular formula would be equal to the empirical formula, which is HCO2 multiplied by, HCO2, and then we multiply all the subscripts there in that formula by 2, and the formula becomes H2C2O4. And that's basically how that is done. All right. Okay, any questions about this one? Any questions? Any questions? All right. So I take it it's okay for me to clear this, and then we scroll down to B part. Now the B part is a bit more complex because in the case of the B part, they gave you some data. And the data is basically the percentages of the different elements present in this compound, right? So basically, it says here that the percentage of carbon is 75.69%, that of hydrogen is 8.80%, and that of oxygen is 15.51% by mass. And it also gave you the molar mass of the compound, right? Now, if you watch the videos that I've posted, I've gone through at least 2 examples, if I remember correctly, of problems of this type, right? And I clearly remember stating that if you're given the percentage values of the different substances, then what you can do is assume that you're working with 100 grams of the compound. Because if you assume 100 grams, that means that each of these percentage values would be the mass in grams per 100 grams, right? So I like to do it in a tabular fashion, where at the top of the table, I put the symbol of the elements. And then the next row in this table would be the mass, which, as I said before, would be the same as the percentages, right? So for carbon, that is 75.69 grams. For hydrogen, that is 8.80 grams. And for oxygen, that is 15.51 grams, right? So that's the first thing we do. We write down the masses. The next step is that we determine the mole value for each of these. And the way we do that, of course, is that we divide each of the mass in grams by the respective molar masses. So in the case of carbon, that would be 75.69 grams multiplied by 1 mole of carbon divided by 12.01 grams. We do the same thing for the hydrogen, 8.80 grams multiplied by 1 mole divided by 1.008 grams. And then finally, in the case of oxygen, it's 15.51 grams multiplied by 1 mole divided by 16.00 grams, all right? So we have to work out each of these. So 75.69 divided by 12.01. And according to my calculations, this works out to be equal to 6.302 moles. And then we do the same thing for the hydrogen, 8.80 divided by 1.008. And according to my calculation, this works out to be equal to 8.73 moles. And then finally, in the case of oxygen, it's 15.51 divided by 16. And according to my calculation, this works out to be equal to 0.9694 moles, all right? So that's how we do that. The next step is where we try to find the simplest ratio of, I should say the simplest mole ratio of these elements present in this compound. And the way we do that is that we look at each of these mole values here and we choose the one that is the lowest, right? Which would be the 0.9694. And then we divide each of them by that lowest value, right? So here I'm going to write down divide by 0.9694 moles, right? So in this case here, it's 6.302 moles divided by 0.9694 moles. We do the same thing here, 8.73 moles divided by 0.9694 moles. And then this divided by itself will give you 1, all right? So let's work out what the other two will give. Starting with the carbon, 6.302 divided by 0.9694. And according to my calculation, this gives 6.501 no units because the mole values will cancel out. And then for the hydrogen, 8.73 divided by 0.9694. And according to my calculation, this works out to be equal to 9.01. All right. Now, at this stage, what you might be tempted to do, especially based on the examples that I've worked out, is that you'll be tempted to round this up to the nearest integer. All right. But this number here is too far from an integer, right? 6.5 is actually smack between 6 and 7. Now, if it was something like 6.9, right, then you can just simply round up to 7. All right. But you can't do that in this case. What you should do is that you should multiply that number and all the numbers that are given in the last row here by an integer, which will convert that number into an integer or an integer, or a number close to an integer. So, in fact, whenever you have at this stage a 5 after the decimal point, so 6.5, 7.5, whatever, what you need to do is multiply right through by 2, right? Because when you multiply right through by 2, this becomes 13 point, 0.00. This becomes 18.0, and this is 1, right? And therefore, these are now integers basically, 13, 18. So therefore, the empirical formula can be written based on these numbers here. So therefore, it's going to be C13, H18. Oh, by the way, this should be multiplied by 2, so this should be 2. I'm sorry. So this would be C13, H18O2. All right? And that's the empirical formula. But we're not finished yet because the question is asking for the molecular formula, right? So how do we get the molecular formula? Well, if you remember what I said first, earlier in the early example, you're going to need the integral factor. Remember the integral factor? Somebody's asking a question. What is that? Okay, so somebody's asking, why are we dividing by the smallest number again? Okay, so the purpose of dividing by the smallest number is to try to get the smallest ratio of the atoms of the different elements present, right? Or the moles of the different elements present, right? So the way we do that is that we divide right by the smallest number, and then we deal with the numbers resulting from that, all right? So I hope that answers your question, Ms. Jones. Yes, ma'am.
How do you know what to multiply by? So like in this example, we multiplied everything by 2.
Right, exactly. I'm going to come to that later on. That's a good question. That's a good question. All right. Okay. What was I saying? Oh, right, the integral factor, right? We need to calculate the integral factor, which, if you remember, I said is the molar mass
Yeah, who's the
by empirical formula
You
mass.
take food. Try thought I should if one with food.
So
Why couldn't me? Because it was probable. Probably all of things. One more folks.
okay. So to get the integral factor, we need two things: the molar mass, which is given already, right? But we need also the empirical formula mass. How do we get that? By calculating the value based on this here, the empirical formula. So let's see here. 13 times 2.01 plus 1.008 times 18 plus 32. And guess what? According to my calculation, the empirical formula mass is equal to 206 0.27 grams per mole. All right. So that means that the integral factor would be 206 grams per mole divided by 206.27 grams per mole, right? Which is approximately 1. So what does that mean? That means that the molar mass, that means that the molecular formula is the same as the empirical formula, which is C13H18O2. And sometimes that happens, right? Sometimes the empirical mass and the formula mass are the same, in which case the integral factor is 1. All right? Okay, any questions before I answer a question? Any questions about this problem? Any questions? Any questions? Any questions out there in Zoom? Okay, so somebody asked a very important question. How do we know what to multiply by at this stage right here, right? As I said before, in this particular case, 6.5 is too far from an integer to just round up to 7, right? So the answer lies in what comes after the decimal point in these numbers. So let me clear this so that I can explain further, right? Now, if you have, I'm trying to think of how to construct this table here. So, if you have a number which has a 5 after the decimal point, then you're going to multiply by 2. All right? So if it's like 2.5, 3.5, whatever, anything 0.5, multiply by 2. If you have a number which has 2 5 after the decimal point, then you multiply by 4. All right? If you have a number followed by 7 5 after the decimal point, then you multiply by 4. All right? What else? If you have a number where you have a recurring 3 after the decimal point, then you multiply by 3. Here. All right? If you have a recurring 6 after the decimal point, you multiply by 3. And if you have a recurring 1 after the decimal point, you multiply by 9. And I think that is it for the ones that we can easily determine. Now, for others, to be perfectly honest, you have to do trial and error, right? Try different numbers. Like, 3, well, we know what 3, we know where you multiply by 3, it goes through circumstances. But there's some like 7 or some other number, then you just try until you get the right integer, which will convert that number into an integer. typically we do that when these numbers here is far from the nearest integer by about, I would say 0.2, 0.1, all right? So that's how you do that. Okay, so let's see here. Let me clear this here and move down to the next question. Okay, so in this case, they did not give you percentages, but they gave you the masses of the different elements present. And pretty much it's the same way as we did before. The only difference is that you get the exact masses, whereas in the previous example, you were given the percentage, right? So again, it's the same approach. I'm going to construct a table here. It's iron, sulfur, and oxygen are the elements. And then I'm going to write the masses for each of them. So for iron, it's 0.0134 grams. For sulfur, it's 0.00769 grams. For oxygen, it's 0.0115 grams. All right. So these are the masses. All right. Okay. So based on what we did before, what would be the next step? Anybody? You can look at the previous example to help guide you. Mole, all right? So how do we get the moles in each case? Let's start off with the iron. It's 0.0134 grams multiplied by 1 mole over the molar mass of iron. We have a couple of here in here, so 55. Oh, okay. Iron 52. You can see from here. Okay, so it's 55.85. 55.85. Okay, and then for sulfur, 0.00769 grams. Just 1 mole over, what's the molar mass of sulfur? That's 32.07 grams. And then for oxygen is 0.0115 grams multiplied by 1 mole over 16.00 grams. So now we need to do the number crunching, 0.0134 divided by 55.85. And I got, okay, I did something wrong. 0.0134 divided by 55.85. Actually, that was correct. Okay, so I got, and please correct me if I'm wrong, but I got 2.40 times 10 to the minus 4 moles, right? And then in the case of sulfur, it's 0.0076 divided by 32.47. And I got for this one 2.37 times 10 to the minus 4 mole. All right. And then in the case of the oxygen, 0.0115 divided by 16, I got in this case 7.18. I'm sorry, 7.19 times 10 to the minus 4 mole. All right. Okay. So what next? Now that we have the mole values for the different elements, what will be the next step? Divide by the smallest number, which is what?
2.37 times.
2.37 times 10 to the minus 4 moles, right? So we divide 2.40 times 10 to the minus 4 moles, excuse me, divided by 2.37 times 10 to the minus 4 moles. This divided by itself will give you 1, and then we divide 7.19 times 10 to the minus 4 moles, divided by 2.37 times 10 to the minus 4 moles. Okay, so this gives 1, 2.40 divided by 2.37 gives 1.01 times 10 to the minus, I'm sorry, 10 to the minus 4 cancel out. So let's erase this here. And as far as the oxygen is concerned, 7.19 times 10 to the minus 4 divided by 2.37 times 10 to the minus 4. This gives 3.03. So in this case here, these numbers are very close to integers, so we can just basically approximate them to the closest integer. So that would be 1 and this would be 3. So therefore, the empirical formula is equal to FeSO3. And that's how that is done. All right? Any questions about this one? Any questions? Any questions? Questions? Any questions out there in Zoom?
What if,
What if?
okay, so I'm sorry, I'm saying this wrong, but you see, what if it was, never mind, it's a hypothetical, I'll find it. Sorry.
You sure?
What if it was like
Uh-huh.
times 10 to the negative fourth power divided by 3? What if it's divided by different?
I'm sorry, repeat that.
I'll figure it out later. Thank you. Sorry.
All right. Okay, any other questions or? Yes, sir.
So when you guys like round up the integer, at what point do you like not round up?
Yeah, I would say, if the difference between that number and the nearest integer is, I would say about, I would say about 0.1. All right, if it's 0.1, then you start looking at multiplying by a particular integer to convert it into an integer. Okay, all right, so let me clear this. Okay, I'm gonna leave number 3 for you to do. If number 3 is very easy. Let's see what number 4 is. Number 4 is also very easy. You should be able to do those too. And let me see here. Number 5 is similar to what we saw just now. In fact, you know what? Let me do number 5 for you guys and then, okay. So it's the same approach. So let me start off with, again, it's carbon, hydrogen, and oxygen. All right. So again, in this case, they gave us the masses. So carbon is 0.62069 grams. Hydrogen is 0.103448 grams. And oxygen is 0.275862 grams, right? So those are the masses. So the moles, of course, we divide each of them by their respective molar masses. Okay, so in the case of carbon, 0.62069 divided by 12.41, and I got 0.05168 moles. And then in the case of hydrogen, it is 0.103448 divided by 1.008. And I got 0.1026 moles. And then in the case of oxygen, 0.2758862 divided by 16.00. And according to my calculation, this gives you 0.0 0.1724 mole, all right? Then we divide right through by the lowest value, which is which one? The oxygen, so divide by 0.01724 moles. So this will be 0.05168 moles divided by 0.01724 moles. Here we divide 0.1026 moles by 0.0174 moles. This divided by itself will give you 1. So let's see what these give. So 0.05168, excuse me, divided by 0.01724. Okay, so this is what I got. I got 2.998, right? And then in the case of hydrogen, 0.1026 divided by 0.01724. And I got here 5.951, right? So obviously this is close to 3. This is close to 6. So therefore the empirical formula will be C3H6 O. That's it. All right. Okay, any questions about this one? Any questions? Question? Any questions out there in Zoom? All right, so that's pretty much it for this assignment. So I was thinking that if you have not done the test already in the testing center, and if you have somebody else question. Okay, Ms. Jones, I'm not sure what you're referring to. You're referring to this question right here that we just completed? Okay, I'm not hearing or seeing anything from Ms. Jones in response. Oh, okay. All right, so what was I saying? Yes, your test. So if you have not done the test already, the test is available in the testing center. And I don't know if you guys saw the announcement I posted. Basically, you need to look out for, because of past issues that we have been having. At the top of the test, on the first page, top of the first page, it should say fall 2025 test number 2, right? I do that so that you don't get the wrong test. In the past, I've had students getting tests from previous times or previous semesters. Also, I've made sure that I've counted the number of pages, right? 6 type pages, including the front page, all right? So if you get a test with less than that, then speak up, all right? Let them know that you should have 6 type pages, right? And also, again, this has been an issue. Make sure that you're given the 75 minutes needed, if you need it, all right? I don't know if I told you guys, but one student told me that she only got 45 minutes or something like that, so that should not happen, all right? So make sure you look out for those things and speak up for yourself, and if, even after speaking up, if there are any issues, let me know, all right? As soon as possible. Okay, so as far as the test is concerned, the test will cover chapters 4, 5, and 6. All right, 4, 5, and 6. And you see here. 4 deals with element atoms and so on, and ions. 5 deals with nomenclature, and 6 deals with chemical equation, right? So all those topics will be covered in the test, and I think there are 3 questions, I don't remember how many questions, but at least 3 questions, and you have to do all of them, all right? So, if you have any questions about any, of the topics I just mentioned, now would be a good time, since I have time, we know my next class, which starts at 12:30. So any questions concerning any of the topics in chapters 4, 5, and 6? And that include you guys out there in Zoom. In the meantime, I'm going to publish the videos for the next chapter, which is chapter 9. Which deals with stoichiometry and the related topics of limiting reactant and reaction yield. So make sure you watch these videos in preparation for the next class, all right? So that's chapter 9. Okay, so if there are no other questions, that's pretty much it for today, folks. See you next week. Yes, sir. Spirits. Okay, and for you guys out there in Zoom, I'm signing off.